Okay, my name is Jana Skama. Here's the student ID. Okay, so for part 1 of lab 3, we're identifying stereochemistry using the molecular model. See, it's all labeled here with hydrogen in the back. I try to find the R and S configurations. So for A, I found that it was S by assigning the priorities for being the lowest with hydrogen. And that goes along with all of them. So with B, I've designated as R configuration, C also, A and the original both S configuration. When it comes to identifying which ones are identical, which one are enantiomers, I was honestly a little confused, so I tried to use the Fisher projections. Since the wedges and dash seem to be identical to A and C, I decided that those are identical, and the other two as enantiomers. Okay, moving on to the actual lab portion, or part 2 for the lab. I've already found the extinction point, and so I've marked it with, I marked the corners with a sticky note. So the first one I'll do is, let's see, I think the first one is alanine. So with the alanine, I still have a bit of the solid left. Maybe focus that. Anyway, so I'll pour that in the beaker first. Making sure to avoid any of the solid. Okay, once that's poured in, I'll measure it for the height of the liquid. It's about 2.6 centimeters, and then I'll convert that to decimeters. Okay, so then I'll put the first sheet on. This is the okay, here is the 0 point, and then we'll be rotating it until we see the extinction point again. So that about there is the extinction point. We'll line up the 0 to the corner where it was originally at. And then we'll turn this. Oh. Seems to be a 90-degree angle. So then I will pour this out and then do the next solution. Okay, the next one is the dextrose solution. So I'll go ahead and pour the whole thing since there weren't any solid left. Again, we'll measure this first real quick. The height is about, let's see, about 2.6 as well. Okay, so I will find the 0 point again. And then I'll rotate it until the extinction point. This already seems to have a farther angle. We'll call it there. Do the same. Started here. Where's the 0? Started here. This angle seems to be about, oops, slightly bigger at 100. And then we'll do the last solution. Okay, the final solution is the fructose. So I'll pour that in there and measure it. This is probably also going to be about 2.6 centimeters. Yep, 2.6. It's consistent with the other two. Okay, so here is the 0 point. Again, we're going to rotate it until we see the extinction point. Okay, this seems to be a little less than 90 degrees. So we'll just line this up at the bottom since it's a little off. Okay, since I started at this bottom corner here, I'll line it up. This will probably end up being a little less than 90, I think. Rotate it. It's approximately 80 degrees, so it is the shorter angle of the three. Okay, so when it comes to the discussion questions, the polarimetry that measures the rotation of polarized light as it passes through an optically active fluid. In this case, since results were gained within all three fluids, I would consider all three of these optically active fluids. So, for the second question, why do the various compounds alter the results? I would think that the density has something to do with it. When it comes to the difference in numbers, the alanine solution had a far more concentrated sample, since it's still pretty visible inside the tube anyway, the solids. So since it's more concentrated or saturated, the number was expected to be higher. In this case, we got these numbers. At first I was thinking that the original concentration would have something to do with it, but I guess the combination, the concentration and how saturated it is, would also affect the overall specific rotation. That being the case, that would mean that the optical rotation then depends on the number of molecules encountered by the light during the whole experiment. In order for this phenomenon to be observed, we have to first see that there is an extinction point, like so, and then it goes back to being a 0 point, so that way an angle can be used to calculate the specific rotation. Okay, so now I have calculated the percent error. I got crazy high numbers for this one, so I'm just going to say I was completely off since the rotations are very different from each other. Here we had an 81% difference and a 15% difference, since these numbers are pretty close and these aren't, I guess, too bad. And then real quick, I guess I'd like to add the explanation of how this occurs. So at the bottom, we see that the light goes through and it hits this first layer. The light goes through it goes through the solution when there is some in here, and then goes to the second layer here. So if the substance is optically inactive, the plane of the polarized light will not change, and so that the angle that we record with this would be 0 degrees. So then if it is optically active, as all three of these were, the plane of the light would be rotated on its way through the tube, or not the tube, sorry, through the beakers and through the two layers here. And then we would actually be able to, I guess, calculator find the angle. And after going through this, I noticed that there is a difference between going the positive direction, which would be clockwise, and the negative direction would be counterclockwise. I'm not exactly sure what the difference is after doing some research. I guess it depends on the compound itself, so I'm not sure. I'm sure that if I had done this counterclockwise, I guess I would have gotten negative 80. So I still think it's pretty close to the actual observed or theoretical value here. So once again, here is a clear shot of the table I ended up getting. One more time, here's the student ID. And then one more shot of the molecular model that I made for the first part of this anyway.